All right, let's look at this classic proof that the square root of 2 is irrational. We need some tools for this, so we'll just lay some of them out here at the beginning. First of all, remember a number is rational if it can be written as the quotient of integers. So it can be written as a quotient where p and q are integers. A number is irrational if it can't be. Another thing that we need, an even number. So an integer is even if it can be written as 2 times another integer, so where k is an integer. And a number is odd, or an integer is odd, if it can be written as 2 times k plus 1 for k some integer. We also accept that an integer cannot be both even and odd. It's got to be one or the other, or integers. Another thing we need is that if p squared is even, so an even integer, then what's also true is p is even. And let's see why that is true really quickly. So let's just do a quick proof by contradiction. If we assume p is odd, that is not even, then p is equal to 2k plus 1 k some integer. All right, this would mean p squared is equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1, or 2 times 2k squared plus 2k plus 1. We also accept that the sum, product, and difference of integers is an integer. So this right here is also an integer. So it could be written as 2p plus, oops, not p, can't use p. We'll say 2r plus 1, where r is an integer. And this means p squared is odd. But that is a contradiction to our given. P squared is even. So by assuming, if p squared is even, and we assume p is odd, we get a contradiction. Therefore, p is even. When p squared is even, so too is p. All right, so those are the tools that we're going to need for the proof. Let's clear this off. So we're going to do this proof also by contradiction. We're going to assume, it's going to be our assumption, we're going to assume that the square root of 2 is rational, so it's not irrational. All right? Well, that assumption means the square root of 2 is equal to p over q, where p and q are integers. Now, as we all know, if we have two integers, or a quotient of integers, we can write something in several forms. For example, 1/2 can be written as 4/8, can be written as 3/6, can be written as 10/20, and so forth. But in all of those cases, we can reduce back down to 1/2. All right, so we're going to make another assumption about our square root of 2. Not only are they going to be integers, so square root of 2 is equal to the quotient of integers, but we're going to have it in its most reduced form. So that means where p and q share no common factors. Because if I pick common factors, reduce it, and those will be my new p and q. Okay, so no common factors for p and q. All right, that statement means, if I cross multiply, the square root of 2 times q equals p. Excuse me, which also implies, if I square both sides, 2q squared equals p squared. Since q is an integer, q squared is an integer, so 2 times an integer is p squared. This means p squared is even. And what we showed earlier is this means p is even. And that means p is equal to 2 times k, where k is some integer. All right, so back to this statement right here. This means we have 2q squared equals 2k squared, because that's what p is, or 4k squared, If I divide both sides by 2, I get q squared is equal to 2k squared. And that means, since k is an integer, k squared is an integer, this means q squared is even. And as we saw above, this means q is even. And that is a contradiction because we assume p and q were in its reduced form, which means p and q cannot both be even. So that is a contradiction, which means our assumption is false. That is, the square root of 2 is not rational. Excellent.